All right, I'm going to go straight through these last examples. Hopefully you had the chance to try the second to last one on your own. This one is kind of like one of those separable equations that we looked at the top of the page. So the first thing that I would do here is I would solve to get y prime by itself. So I would rewrite this as y prime equals, we're going to add 3y to the other side. And then I would probably go back and rewrite that as dy dx. So dy dx equals 3y. Again, our goal is to multiply both sides by dx. So we get dy equals 3y dx. And there's no other x's to worry about. The only thing we need to do is get that y to the other side. So by dividing both sides by y, we can do that. Oops. So we get 1 over y dy equals 3 dx. All right, so that's the first step, to separate. The second step is to integrate. I'm just going to change, maybe, well, I'm just going to try to change pen color. I'm having technical difficulties. All right, so from this step, if we integrate, I'm going to pop this up here. When we integrate 1 over y dy, we know that that's going to be the natural log. Oh my goodness, this is not the time for my pen to stop working. The natural log of the absolute value of y. And on the right-hand side, when we integrate 3 dx, that's just 3x. Don't forget the plus c. I said it earlier, if you forget the plus c, the AP graders will stop grading your question if this is an FRQ, so we can't forget the plus c. All right, so far we have separated and we have integrated. We could now try to find c. I'm just going to go out here to the side real fast and try to find c as best I can. If we try to find c, we're plugging in 1 for x and 4 times e to the 5th for y. So I'm going to have the natural log of the absolute value of 4e to the 5th. Well, I know that's a positive number, so I could really drop the absolute value there, equals 3 plus c, 3 times 1 plus c. So we're going to get like that, the natural log of 4e to the 5th minus 3, that's equal to c. And it's not that that's wrong, but that's really messy. When we get to a c that looks really complicated like this is where I would actually just maybe back up and say, hey, maybe it makes more sense to solve this for y first. So I'm actually just going to go back and solve this one for y. So from the equation that we got when we integrated, if we solve this for y, we know we've got to exponentiate both sides. Sorry, trying to record and write at the same time is harder than I thought it would be. All right, so we're going to exponentiate both sides. We know that gives us the absolute value of y on the left, and on the right-hand side, e to the 3x plus c. Remember what we said before about those exponent rules, that when I have e to the 3x plus c, I could rewrite that as e to the 3x times e to the c, and e to the c is just some arbitrary constant c, since we don't know what c is. So I'm going to put the c out in front. Same thing we said when we get rid of the absolute values, absolute value bars, technically this is plus or minus c times e to the 3x. But again, because c is just some unknown arbitrary constant, since we don't know yet if it's positive or negative, I can just absorb the option that it's negative into the constant itself. So we could drop the plus or minus. Now we can't just go around dropping pluses or minuses normally, but again, it's because we know that c is a constant. We just don't know what it is. So we'll find out soon if it's positive or negative. All right, so we've isolated y. Y is all by itself. Now we could plug in our initial condition to figure out what c is. So I'm going to substitute. I'm going to just change colors to kind of track my thought here. I'll try this color blue. I'm going to substitute 4e to the 5th in for y. 4e to the 5th. And that equals c times e to the 3x. So e to the 3 times 1. And now to find c, it's going to be so much easier. We can just divide both sides by e cubed. Having a really hard time. When we do that, 4e to the 5th divided by e cubed is just 4e squared. So that's a much nicer c to work with. All right, our final steps, just putting this all back together. I can't end with c. I've got to rewrite my equation. Y equals c, so 4e to the 2nd times e to the 3x. And then we could leave it that way. I mean, that's fine, that's correct. But just remember, we can clean that up using those power rules, that since we have two powers with the same base e that are being multiplied, we can add their exponents. So I might write that like 4 times e to the power of 3x plus 2. And that would be our final answer, although both of those final answers are correct. All right, this last question is one last question we're going to do. Sorry, I thought I heard someone knocking at my door. Last question. The rate at which a population grows is proportional to the population itself. If the initial population is p of 0 equals p sub 0, or maybe we could call that p naught, find the function p of t that models the population for any given time t. Lots to unpack here. We're given the description of the differential equation. So the rate at which the population grows, that's the description of the differential equation. We are told that it is proportional to, and we're told that it's proportional to the population itself. Ooh, so let's try to unpack that in a couple of pieces. All right, the rate at which the population grows. So I'm going to think of this as the rate at which the population is growing with respect to time. So I'm going to think of that as like dp over dt. When we say something is proportional to something else, it means that there's a constant of proportionality or a constant multiplier. So I'm going to let that constant be k, and then it's proportional to the population itself. So since p represents the population, it's proportional to p. So if we go back and kind of unpack this one piece at a time, we said the rate at which the population grows, that's modeled by dp dt. When we say that it is proportional to, we're going to have our constant of proportionality times the thing it's proportional to, the population. Okay, so now we have a differential equation, which again, the procedures are pretty much the same. This is actually really similar to the last one we did. We'll see that in just a second. All right, I'm going to multiply again both sides by dt. So we get dp equals k, which is a constant of proportionality, times p, the population itself, and then the dt gets multiplied to the other side. So we're in that first step where we want to separate. Well, k is just a constant. The only thing that needs to move is the p. So divide both sides by p, 1 over p dp equals k, our constant of proportionality, times dt. All right, separate, then integrate. So now we can find ourselves at the integration step. On the left side, when I integrate 1 over p, that's just the natural log of the absolute value of p. And remember, again, k is a constant. So when I integrate a constant with respect to t, I get that constant times t plus c, my constant of integration, not the same as k, the constant of proportionality. From here, this looks a lot like the last problem. I can tell if I try to plug stuff in right now to solve for c, it's going to get messy. So I think we should actually just solve this one for p. All right, so we can do that again by exponentiating both sides with a base of e. When we do that, all that junk is in our exponent. And then on the left side, I have the absolute value of P, and that equals e to the power of kt plus c, k times t plus c. Just like the one above, we could use those power rules to, I'm not going to go through all the steps, but we could use the power rules to rewrite that as the product of two different powers. And then we'd be able to just change e to the power of c to just c, some other constant that we don't know. All right, and then same as before, we can drop those absolute value bars. And again, we don't really need a plus or minus here because c is an arbitrary constant. We don't know what it is. Maybe it's negative. We don't really need to consider both cases. So we get this formula, or this equation rather. So we solve for P. We do need to go back in and plug in our initial condition. So for our initial condition, when t is 0, P is P sub 0, or I might even read that as P naught. All right, so if I go ahead and plug this in, we said that when t is 0, P is going to be P sub 0. All right, so k times 0 is 0, so e to the power of 0 is 1, and we really just get that c then, our constant, is P sub 0, is our initial population. All right, so if I go back to rewrite my equation, I've got that at any time, our population P is our initial population, P sub 0, because that's what we got for C, times e to the power of kt. And that's it. That's our final answer there. And when you guys took Algebra 2, you did some work with equations. This might look familiar. Do you remember? Remember this equation? Sometimes we call it APERT. You use this when you're continually compounding interest. Well, population growth really follows the same model, that this e to the rt, when you use this for compound interest, r represents the rate of your interest, t is time, and p is like your initial quantity. So really this population growth is going to follow the same model. So when you guys learn that in Algebra 2, you don't obviously you don't learn it via differential equations, but that is how those two things are related.